Okay, so last week we have finished the first set of PowerPoint, and I remember that we somewhere stopped at this slide. So after explaining the schematics diagram, then we ended the lecture. So today in this tutorial, I hope that we have time to finish most of the PowerPoint for this session. Okay. So if you remember, we have spent quite a long time, quite a lot of time on this schematic diagram, because this schematic diagram is very, very important. Okay, it is like a map to show you how electricity will be distributed from the origin of electricity. So from the point of view of the electrical designer, the origin of electricity is the main Lv switchboard. Okay, so in this diagram, as shown in the center line box here, this is the main Lv switchboard. Okay, so the main Lv switchboard receives the electricity from the transformer, which has been stepped down already. So the voltage output from the main Lv switchboard is 380 volt three phase and 220 volt single phase. All right. So from the main Lv switchboard, the electricity will be distributed to different current using equipments like the chiller plants, the water pumps, the lift, the escalator, or some other distribution boards, to the tenants, to the landlords, and so on. All right. And we have also learned that in this schematic diagram, there are different types of loading. We have the normal load, okay, which are the load supplied from these green bus bar, okay, these green color conductors. So the loadings like the chiller plants, these distribution board, the restaurant, the tenants, the escalator, the exhaust fan. So all these are normal load. So the term normal, which means that they are non-essential. So in case of power outage, in case of fire, no emergency generator will be used to back up these loading. Okay, so we don't have power for the chiller plant, for the exhaust fan, for the escalator, for the shops and restaurant, and so on. Okay, so they are non-essential load. And for the loading supplied from this red bus bar, they are essential. So essential means that they are very important. So in case of power outage, in case of fire, the emergency generator will be used to back up power. Okay? So non-essential, or we call that normal load. And the other type is the essential load. And apart from non-essential and essential, we may also classify the loadings into tenant and landlord. Okay, so for the tenant load, it means that the electricity power company will install individual energy meter for each tenant. So each office tenant, each shop tenant, each restaurant, they will pay for their own electricity fees, right? So in this diagram, we have these two restaurants, the office tenants, the shops. So these are tenant load. So the equipment, the lighting, the small power inside the restaurant, inside the office, inside the shops, they are the tenant load. Okay? And for the rest of the loadings, they are all landlord. Okay, landlord load. Like the chiller plants, the water pumps, the air conditioning, and also the small power and lighting for the landlord. For the lift lobby, for the toilets, for the entrance lobby, and so on. And the escalator, the exhaust fan, the passenger lift, and all these the fire services equipment, the fireman lift. So all these are landlord, and their electricity power consumption will be measured by this meter and also this meter. All right, so these two energy meter will measure the energy consumption by the landlord, and the building owner will pay for the electricity fees. But of course, they will charge the tenants the management fees and so on. So it means that it doesn't mean that the tenants doesn't need to pay for the electricity's consumption, for the air conditioning, for the water pump, for the passenger lift. Actually, the landlord will charge management fees, right? So part of the management fees would be the electricity consumption in the landlord area. Okay, so but this is not the main point for our lecture. All right, so this is what we have learned in the lecture last week. Then let's carry on. So we have loading estimation. So according to our assessment scheme, one of the assessment component is the mini design project, right? So I haven't uploaded anything about the mini design project yet, but in the mini design project, part of your task is to estimate the electrical load in a building. Okay, so when you receive your mini design project, you will need to come to read again this set of PowerPoint, because this is about your mini design project. Okay. When a consumer makes an application to the supply company for electricity supply, so just like a client would like to build an office building, so he is applying electricity from CLP, okay, the China Light and Power. Then he must declare the quantity of electricity. So CLP will ask, how much electricity do you need? 5,000 kVA or 10,000 kVA, so how much? So the declared quantity of electricity required is to enable the supply company or authority to make provision for and to install all the necessary equipment to meet the consumer's requirement. So for example, the office owner, okay, said that I need 5,000 kVA. Then CLP will estimate how many transformers do you need, and then I will provide you how much electricity and so on. And for the building owner's point of view, they also need to reserve a big enough plant room for the transformer. Okay, so they have to reserve a large enough room and to satisfy all the requirements by the utility company. So this electrical loading should be as accurate as possible. Okay, so a higher than required declaration. So if you overestimate, then it means that you need to reserve a larger space. Larger space means more expensive. Okay, and you also need to provide a larger cable, larger equipment, so everything larger. So it will be more expensive. Okay, so for example, the office building, they apply for 5,000 kVA, but in fact, they don't need 5,000, they just need 3,000 kVA. So overestimate a lot. Maybe originally they only need 2 transformers, but now they have installed 3 or 4. And the transformers room is much, much bigger than required. So it will be wasting money, right? And if the actual requirement is less than the declared value, the consumer may have to pay for a penalty. Okay, so if you So you apply for 5,000, but actually you only need 3,000. Then the power company may charge you a penalty. Okay, may charge you a penalty because you are asking more than you need. But how about the other way around? Okay, so I apply for 5,000 kVA, but in fact I need 6,000. So your system will be overloaded. And when the system is overloaded or when overcurrent occurs, the electricity supply will be disturbed. So the circuit breaker may trip and it will cause disturbance to your customers or to the tenants. And you may need to apply for extra electricity, but you need a transformer room. So you need to find another space, another very big room for the transformer, and then to install all the associated cable, the equipment. So you may not have enough space, right? So it is better to do an accurate estimation in the preliminary design stage. So the objective of loading estimation is to achieve a realistic estimate of the total building load. And it is for plant planning. Okay, for planning how large should be the transformer room. And then how big should be the main Lv switchboard, and how big should be the bus bar and the cable and the equipment, everything. For the estimation of total building electrical load, we usually use the Admd method. Okay, Admd is for after diversity maximum demand. And it is for preliminary design stage. So in day one, okay, on day one, when you don't have any detailed information about your building layout, so you only know that this is an office building, but then the detailed layout, like on every floor, do you have a open plan office, or how many cellular office do you have? Where are the conference room? What is the layout for the director's room? No, you don't have these details. Or what types of lighting, whether you will be using the fluorescent lighting or the LED, you don't have these information. Okay, you just know that I'm going to build an office building with 20 stories, and what is the floor area. So I only have these rough information. Then we may use the Admd method, and this method can give you a rough number of the total building load. Okay, not for individual floor, not just for an office floor, not just for a restaurant, but for the whole building. All right, for the whole building, then you can estimate how many transformers do you need. Okay, the only purpose of Admd method is to estimate the number of transformers do you need so that you can allocate a large enough transformer room for your building. Okay, so the Admd method is described in the CLP Code of Practice 215. So this is for transformer room reservation, not suitable for the low voltage installations after the customer main switch. So after the main Lv switchboard, you can no longer use the COP 215 to estimate the electrical load. Okay, no. And by using this method, the maximum demand, kVA, will be estimated. Okay, so let's take a look how to use this method. Admd, and the Admd this method can be used to estimate the loading for residential building, for commercial building, or industrial and municipal building. So if it is a commercial building, Then the ADMD is a figure, which is like a loading density. So it will have a table, okay, showing you some recommended loading density for different types of usage. So this loading density is kVA per square meter. Okay, so kVA is the apparent power. There are three types of power, right? In the power triangle, where when you calculate a power factor is the active power divided by the apparent power. So we have the active power, the apparent power, and the reactive power, right? So the units for active power is kilowatt. P is kilowatt. And for kVA is S, apparent power. So power factor is P, kilowatt, divided by the apparent power, kVA, right? So remember, this is not the active power, kilowatt, but kVA. Okay, kVA per square meter. And we may use the same document, COP215, to calculate the loading for other types of building. And if your building is using central air conditioning, like the chiller, and then you have the VAV distributing the cool air, then we have some special estimation. So cooling load estimation, and so I will explain in the coming slides. Okay, this is the table extracted from the COP215. And these are ADMD figures for residential development. And this one for commercial development. For commercial development, we have different types of usage, like general shops, catering, okay, or general shop non-catering. And we have hotel, office, cinema, and so on. Okay, so these values, the unit of these values would be kVA per square meter. Okay, so they are just like loading density. So I have a building with 20 floors of office. So I will calculate the total electrical load in the office by multiplying 0.16, right? For office, 0.16, and then multiply with the area. So it would be the electrical load of all the offices. Okay, so very straightforward. Just a loading density value multiplied by the area, then you have the kVA. And in the bottom, we have an item called public services. And the value is 40 kVA per lift. 40 kVA per lift. So this is not a loading density in area. Okay, not the density in area, but it is in terms of the number of lift. So here, what does it mean by public services? Public services would include the passenger lift, the water pumps, and also some fire services equipment, the lighting and small power in the public area. Okay, for all these public services, it can be estimated based on the number of lift. So here, this is just an assumption. So for CLP, this document, the ADMD method, is recommended by CLP. And CLP has a very, very big database because all the buildings in the new territories, in Kowloon, in Lantau Island, would be supplied by the CLP, right? So they have a very big database, and they find out a correlation between the public services load and the number of lift. So they find it if a building has more number of lifts, then the public services loading will also be larger. So they are like having a linear proportional relations. So CLP recommend to use 40 kVA per lift when you want to estimate the total electrical load of the public services. Okay? So here, 40 kVA is not the power consumption for one lift. No. Not just lift, but many other public services. Okay? Because usually students may misunderstand. So he may think that 40 kVA per lift, then it means that for one lift, the power consumption would be 40 kVA. So it's not. The power consumption for one lift is usually much less than 40 kVA. Okay? And one more thing that I want to remind you is about the area. So for these ADMD figures, they are loading density by the area, right? So here, area, we have many different types of area. We have the GFA, the gross floor area. We have the usable floor area. We have many different type of area. And here, these density values, they apply to the UFS, or we call it UFA anyway, usable floor space area. And according to the building planning regulations, usable floor space means any floor space other than staircase, halls, lift landing, the space used in providing water closet fitment, urinals, lavatory basins, and the space occupied by machinery for any lift, air conditioning systems, or similar services. So it means that when you apply these power density, like for office, make sure that you didn't include the area by the plant room, by the staircase, by the toilets, by the lift lobby, and so on. Okay, so generally, the power density for office will apply to the office area. The office area by the tenants, excluding the lift lobby, the circulation area, the corridor, and the toilets, and so on. All right? So in the mini design project, I will give you an office layout plan, and you need to estimate the total building electrical load for that building. So make sure by that time, when you estimate the area and apply these loading density values, don't include the area of this space. Okay? So in the electrical loading estimation, we have learned two components. The first component is based on the area, kVA per square meter, and then multiply the usable floor space area. The second component is the public services load, 40 kVA multiplied by the number of lifts. Now we have the third component, which is the electrical power by the chilling system. So this third component will depend on the heat rejection method of the chilling system, whether it is a packaged air cool, indirect seawater cool, direct seawater cool, or direct water cool. And different conversion figures will be applied. So for example, in your office building, you are using a air cool chiller. Then you will use the first number, 1.85. 1.85 kilowatt of electrical consumption per ton of refrigerant. Okay, so ton refrigeration is a unit for cooling load. So you will estimate the total building cooling load. And then sometimes your cooling load estimation will be using kilowatt unit. So you have to convert kilowatt of cooling load into ton refrigeration, and then multiply by the number like 1.85, and you will have the electrical power with the unit kilowatt. Okay, and in the previous two components, the unit is kVA, right? In the previous PowerPoint, the unit is kVA per square meter and kVA per lift. So here we have to convert kilowatt into kVA. How? How to convert kilowatt into kVA? Kilowatt is P, the active power, and kVA is the apparent power. So remember, for the power factor, kilowatt divided by kVA. So if you want to convert kilowatt into kVA, then just use kilowatt divided by the power factor, right? So this is the third component in the electrical loading estimation. So let me have a quick revision. So three components. The first one, based on the ADMD value. Like for an office, 0.16 kVA per square meter. So you will use 0.16 multiplied by the usable floor space area. The second component is for the public services. So how many lifts are there in your building? Then multiply by 40 kVA. And the third component is on this slide. If you're using packaged air-cooled chiller, then 1.85 multiplied by the cooling load in ton refrigeration, and then you have to divide it by the power factor. So you have kVA. So the summation of these three components, you have the total building electrical load. All right? So what should be the power factor? The smaller the power factor, the larger would be kVA. We have a particular kilowatt divided by power factor, then we have kVA, right? And the power factor is a number smaller than 1. So the smaller the power factor, the larger would be the kVA. So we may use the smallest expected power factor, which would be 0.85. Okay, in a low voltage distribution system, 0.85 is the lowest power factor. Or I should say, in the main Lv switchboard, the lowest power factor would only be 0.85 because the utility company, like the CLP or HEC, they required their customer to correct the power factor to at least 0.85. Otherwise, they will charge a penalty, another penalty to their customer. So in the main Lv switchboard, we have to install some capacitor bank. So when the power factor is too low, then we will use the capacitor bank to improve the power factor so that it is larger than 0.85. Okay? So when you do the electrical loading estimation, you may assume the power factor to be 0.85. Okay? So the ADMD method is for preliminary design stage when we don't have much information about the building. And when you are in the middle of the project, okay, so when you have more information and you want to do not just to reserve the plant room space for the transformer, maybe you want to estimate or start doing the design for distribution, okay, the electrical system, distribution to the office, to the shops, to the restaurant, then you may want to estimate how much electricity does a restaurant need, does a shop need, does an office need. So by that time, you may use the loading density method. So this is the estimation of overall maximum demand based on loading density. So just similar to the ADMD value. But for ADMD values, which is recommended by CLP, it is only used for transformer room reservation. Okay. So although the concept is similar, but we don't say that I am using the ADMD method to estimate how much electricity does one restaurant needs. No, this is not correct. Okay. So for the loading density method, it is normally used to estimate the total load of an installation. Like for a submain system, which will distribute the electricity to 20 floors of office, I may use the loading density method. Or I may also use the same method to estimate the electricity power consumption for just one office. Okay, so at different points of the distribution system, we may also use the loading density method. It is usually used to determine the switch rating of a distribution board. Just like in your kitchen, you can find the distribution board, right? So what is the main switch rating of your distribution board? Maybe 80 M, maybe 100 M. So this size, the size of the rating, will depend on the floor area. So if your home is very large, then we expect that you will use more electricity, and the main switch should also be larger, right? So the loading density method can be used to determine the switch rating, the main switch rating for a residential flat, for an office, for a restaurant, and so on. Reference data may be obtained from records of past projects of the same type and size. When you graduate and work in a consultant company or other design firm, then they will have a database. So from their past experience, if it is a office, then maybe you can use a power density of 0.2 kVA per square meter, and so on. Okay, so we will refer to the past project with similar nature. The building is not constructed yet. There are no occupants. No occupants have moved into that office. So we cannot measure, or we cannot very accurately estimate how much electricity will be consumed by the future occupants, right? This is impossible. So we can only based on the past project and do some wise estimation. And those tables give only the average value. So for typical office, we may use that number. But if your office have some significant loads that are not found in the average or typical installation, then that table may not be accurate. So this is something you have to be careful. This is the table that I found from a reference book. And this is from another document. So you may just treat them as a reference. Okay, so we have explained the ADMD method, the loading density method, and now one more method, which is called the diversity method. So actually for the diversity method, I am going to explain in the lecture this afternoon, the maximum current or maximum power demand method. So this diversity method will be used in the detailed design stage. When you have a detailed layout plan of the lighting system, of the small power system, just like in this classroom, I have the lighting layout. So I know that in each luminaire, in each lighting fixture, there are 3 lamps, and each lamp may have a power consumption of 28 watt. So I can estimate the total lighting power consumption. And I also have the small power equipment, like the projectors, and then we have the socket outlets, we have the computers. So all these, when I have all these information, using the diversity method, I can estimate the electrical load consumption of this classroom. Okay? So when detailed architectural plans are available showing the usage of each area, so this area for toilets, this area for conference room, and then the open plan office, the director's room, the pantry, and the storeroom, and so on. So when we have this detailed layout plan, and the electrical installations can be divided into lighting, appliances, the air conditioning, small power, and so on, then we can use the diversity approach. The maximum current demand from several final circuits can be estimated by adding the current demand of all points of utilization and items of equipment connected to the circuit, and where appropriate, diversity is allowed. This is a bit complicated, so I think after the lecture in this afternoon, you will understand what it actually means with diversity. Okay, so for the first bullet point, you may need to read it once again after the lecture this afternoon. Okay. So diversity, or maybe I can briefly explain what does it mean by diversity. When you go to toilets, there may be 4 water basins, right? But it is very, very rare that all the 4 water basins are turned on to the maximum flow rate at the same time, right? It's very, very rare. It may happen, but just for a very short moment of time, okay? So when you design the water supply system to this toilet with 4 water basins, maybe you don't need to design the water pipes so that it can allow 4 times of the flow rate of each water tapes. You know what I mean? Because it's very rare that the 4 water tapes will be fully open. And it applies to the electricity. Just like in this floor, we have many, many different classrooms. But it's very, very rare that all the classrooms are used at the same time. So when we design the electricity power supply to the whole floor, we may reduce the power supply, or we may reduce the rated value of the design current. So this is the concept of diversity. Okay, so we will learn once again the concept of diversity this afternoon. This equation will also be explained this afternoon. Maximum demand is equal to the connected load multiplied by the diversity. Okay, so this table I will explain today, later. Transformer room. Using the Admd method, we can estimate the total building electrical load. Maybe the total load is 2,400 kVA. Then we may need 2 transformers. If it is less than 1,200 kVA, we may need 1 transformer. So this is based on the typical power rating of each transformer to be 1,500 kVA. Okay, the typical power rating of a transformer is 1,500 kVA. So if your power consumption is less than 1,200 kVA, then you only need 1 transformer. But why not less than 1,500? Because we are using the Admd method to estimate the loading, and it is not 100% accurate. So we don't want we want to be safe, okay? We don't want to overload the transformer. So when the loading is up to 1,200, not 1,500, just 1,200, we recommend you to use one transformer. And when it is over 1,200, using just one may be not too safe. So we recommend you to use two. So 1,200 up to 2,400, we use two, and then for larger, we use more. Okay. And the requirement of a transformer room, you can refer to the COP 101. COP 215 is for the Admd method, and COP 101 is for the transformer room requirements. So if your building is located in Kowloon or New Territories or Lantau Island, you refer to COP 101. But what if is in the Causeway Bay, is in Central Hong Kong Island? Then you refer to Guide to Connection of Supply by HEC. Okay, 港燈. So COP 101 by CLP and the Guide to Connection of Supply by HEC, they are something similar. Okay, they will talk about similar topics. So requirements of the transformer room. On this slide, I have extracted some general requirements for the transformer room. For example, the substation or transformer room shall be situated at the periphery of the building. So periphery means the perimeter. So you cannot place the transformer room in the center of the building. It is not allowed. Okay, so in the mini design project, after using the Admd method to estimate the total building electrical load, then you should be able to propose how large should be the transformer room. And then I will ask you to draw the transformer room on your layout plan. So by that time, don't draw it in the center of the building because it is just not allowed. Okay, the transformer room should be at the periphery of the building. And for substations on the ground floor, they shall be directly accessible from open air, and it is non-cover anytime, 24/7. Okay, so it should be located in the perimeter of the building, and it should be accessible from the outside of the building anytime without passing through any tenant area or restricted area. All right. No water pipes, drainage pipe, or customer installation shall be located in or passing through any part of and inside the ceiling slab of the installation. So inside the transformer room, everything would belong to the CLP or the utility company, and there should not be any customer installations. Like there should not be any water pipe, right? So above the transformer room, it should not be kitchen or pantry or toilets, because in that case, it may have some wet hazard, some water hazard. And even if it's not water pipes, so maybe right next to the transformer room is the main Lv switch room, and you have a bus bar, you want to cross the transformer room and to the next room, it is not allowed. Okay, you cannot run any cables or bus bar, any customer installation across the transformer room. So it is like a sacred area. Okay, you cannot walk through it. Your customer installation, anything, even not water, you cannot run it across. You cannot run it through the transformer room. Adjacent and adjoining occupancies and hazards must be taken into account, particularly in respect of avoiding wet environment. So near, surrounding the transformer room, above it should not be any plant rooms or rooms associated with water. Not more than 3 transformers shall be accommodated within one transformer room. So each transformer room can only house up to 3 transformers. So what if you have 4, then 2 plus 2, or 3 plus 1, but not 4 transformers in the same room. Okay, the last one. The main Lv switch room shall be located directly adjacent to, above, or below the transformer room. So it is just to reduce the voltage drop. So right next to the transformer room, or right above the transformer room, right below the transformer room, should be the main Lv switch room. Okay, you remember the main Lv switch room, this is where the electricity comes from, okay, in terms of the low voltage installation. So we cannot put them far away, because when they are far away, then we expect a large voltage drop, and it is not good. So we want to reduce the cable run between the transformer room and the main Lv switch room. Some more requirements, and I think I will just skip them and you may read it yourself. Okay, this is the suggested transformer room layout plan, but not the latest one. CLP may revise the requirements from time to time, but anyway, it will be something like that. If you have 3 transformer, okay, this is the transformer, 1, 2, 3 transformer, and this is the building boundary, okay? So this is the outside of the building, and there should be some doors open to outside. This is the latest version. So 1, 2, 3 transformer, and 3 double wings door, another single wing door. And right next to the transformer room, this is the main Lv switch room. So you can see how big should be the transformer room. If you need 3 transformer, so 4,500 kVA capacity, the transformer room has a size of 19 meter by 5.6 meter, which is a very big room, 19 meter long. Okay, and if you locate the transformer room in the basement, it is allowed, but you need to fulfill all these requirements. So I think I will just skip it. You can read it yourself. And you may also put the transformer room above ground floor. So on a first floor or second floor, but once again, there are some additional requirements. So remember, the transformer room should be accessible by the CLP workers anytime, even in the middle of the night. So you have to provide an access to the transformer room above or to the transformer room basement without passing through the lift lobby or the entrance lobby or other area. So these transformer rooms should be directly accessible from the outside of the building. Okay, I think we have to stop here because I can see that someone's waiting outside. So I will see you again in the lecture in the afternoon, 1:30.